Factoring special products. Your learning target. You'll identify and factor perfect square trinomials and the difference of perfect squares. How can I look for and make use of the structure of an expression to classify it by type? So we'll review what we know about squaring a binomial. To square something means multiply it by itself. And now using FOIL or double distributive or the box, you would get the resulting trinomial to be x squared plus 12x plus 36. This trinomial that is in bold is called a perfect square trinomial because it is the result of squaring a binomial. So let's take a look at the structure of a perfect square trinomial. What do we observe about it? Notice the first term is a perfect square, right? X times x will result in x squared. The last term will be a perfect square. 6 times 6 equals 36. And the middle term will be twice the product of the square root of the first and the last term. So remember, the square root of the first term was x. The square root of the last term was 6. 6 times x is 6x, and then when you double that, you'll get 12x, the middle term. So this is true of the structure of any perfect square trinomial. And whenever you find a perfect square trinomial, it factors into a binomial, x, which is the square root of the first term, plus 6, the square root of the last term, quantity squared. Here we're asked to determine whether a trinomial is a perfect square trinomial. And here's the criteria that we're looking for. So let's go through it as a checklist. Is the first term a perfect square? How about the last term? Now when you take the square root of the first and the last term, right, x times 3, you get 3x. If you double that, do you get the middle term? Therefore, this trinomial is a perfect square, and it factors into a binomial squared, namely x plus 3 quantity squared. Now, we don't always have to have plus signs. There can be perfect square trinomials with a minus sign before the middle term. Let's test if this is a perfect square trinomial. The first and the last term are perfect squares. Now take the square root of the first term, you get x. The square root of the last term is 2. Multiply those together, you get 2x. Double that, you get 4x. So no, the middle term is not twice the product. Therefore, this is not a perfect square trinomial. It will not factor into a binomial squared. All right, more practice. This time, though, there's a greatest common factor among the 3 terms of the trinomial. Let's factor the 4 out. And now let's go through our little test of whether or not what's in gray font is a perfect square trinomial. The first is definitely a perfect square. The last term is a perfect square. The square root of the first term and the last term would be 3x times 2, or 6x. If you double that, you get 12x. So yeah, the middle term is twice the product of the square root of the first and last terms. So it will factor into a binomial, but this time the binomial will have a minus sign separating the terms. All right, so I want to transition into difference of perfect squares, our other type of special product that we'll learn to factor. But before we do, let's remember how we used algebra tiles to model x minus 2 as the height of what's going to be a rectangle times x plus 2, that will be the base. Now remember, we looked for algebra tiles that would represent the product of these terms. So x times x would be x squared, the blue square, remember? And recall where all the other pieces inside came from as the rectangle. Now, the product of x minus 2 times x plus 2 is going to be the area of this rectangle. But the area of the rectangle can be simplified because we have two zero pairs for x bars. So we can simplify the product this way as x squared minus 4. And turns out x squared minus 4 is what we call the difference of two perfect squares. Because we have two perfect squares and we're subtracting them, it will factor into those two binomials that you see to the left, x minus 2 times x plus 2. So let's kind of get a handle on the structure of the difference of perfect squares. Well, just like before, the first and the last term are perfect squares. But there is no middle term. Instead, there's a subtraction sign separating the two. It must be a subtraction sign, by the way. We could not do this any factoring if there were an addition sign. So when we factor the difference of perfect squares, notice two binomials will result. It'll be the square root of the first term plus the square root of the second term times square root of the first term minus square root of the second term. And those factors can go in either order. You can put the minus binomial first and then the plus, or vice versa. All right, sometimes you're going to have powers in your difference of perfect squares that are not 2. And so let's consider, would d to the 10th, for example, be a perfect square? Well, can you write it as some expression times itself? Yes. So d to the 10th is a perfect square. And to generalize, it's important to keep in mind, if you have an even exponent as your exponent of your variable, we call that a perfect square variable. So just kind of keep in mind, a variable to any even exponent will be a perfect square. All right, so let's get some practice factoring the difference of these two perfect squares. Remember, it will factor into two binomials. The square root of the first term goes in the first slot. The square root of the second term goes in the second slot. And we use a plus and a minus. These are some of actually my favorite polynomials to factor. They just seem to go so quickly and easily. Here we have the difference of perfect squares. So we'll use two sets of open parentheses. We'll put 3m in the first slot and 4t in the second slot, and we'll use a plus and a minus. All right, so I have two problems for you to try. You can just put the video on pause for a moment. And there's one of each type that we've talked about in this video. So factor these two polynomials if possible. Press resume when you're ready. All right, so the first trinomial is a perfect square trinomial because the first term is a perfect square, the last term is a perfect square. The middle term is twice the product of the square root of the first and the last term. Therefore, it factors into this binomial quantity squared. Now the example in red is the difference of two squares, two perfect squares. So we're going to use two binomials. I've got the square root of 36x squared as the first slot, the square root of 81y to the 10th in the second slot, and don't forget your plus and your minus signs.